Now we will discuss the various properties of a best estimator one by one. The first property is unbiasedness. In the coming sections, we will denote a parameter using theta and an estimator using t. So clearly, a parameter theta is a function of the entire values of a population, while an estimated t is a function based upon the values or the variables representing the sample. An estimator is therefore actually a statistic. Suppose x1, x2, etc. xn be a random sample drawn to estimate the population parameter theta. So we found that these random variables representing sample has to be formulated properly in order to estimate a parameter. That means we have to propose certain function of x1, x2, etc. etc. because the variables separated with the comma cannot propose any any value for the parameter. If we are formulating with some mathematical operators or mathematical functions, then only it can be used to estimate certain parameter. Suppose T is a an estimator. T is an estimator proposed to estimate the parameter theta. When do you say that T is an unbiased estimator? T is said to be an unbiased estimator if mean of T is equal to theta. In sampling distribution, we found that the statistic will be always a variable while parameter will be a constant. And since t is a variable, there will be definitely a probability mechanism governing the variability of t. And that probability mechanism is known as sampling distribution. Therefore, if the mean of all these variables t is theta, then t is said to be an unbiased estimator. Or if the mean of the sampling distribution is theta, then t is said to be an unbiased estimator. Mean of a variable and mean of the respective distribution are same. Therefore, t is said to be an unbiased estimator if this expectation of t is equal to theta, or this mean of the distribution followed by t is equal to theta. Now let us consider an example to examine this unbiasedness property. Here we propose an estimator x bar proposed to estimate population mean mu. So x bar is the sample mean and mu is the population mean. We can note that this x bar is a function of the values belonging to the sample, while mu the parameter, which is a function of the entire values of the population. In order to show this x bar is an unbiased estimator of population mean, we have to prove that actually the equation E of x bar equal to mu. That is, this x bar is in the place of t and mu is in the place of theta. Yes. Using this expectation, we have E of x bar equals E of 1 by n, sigma is equal to 1 to n xi. In expectation, we have a property that E of AX equal to A E of X. Here 1 by n is a constant. So 1 by n can be taken outside this E operator. That is why 1 by n into E of x1 plus x2 plus etc plus xn. This x1 plus x2 plus etc plus xn is obtained by expanding this summing operator. Now we have another property in expectation that expectation of a sum is sum of expectation. That is E of x plus y is equal to E of x plus E of y. I shall also note down the two properties applied in expectation to verify this uh, unbiasedness of unbiasedness of x bar. So the first property is expectation of Ax is equal to A expectation of x. That is, if A is a constant, A can be taken outside and E is to be applied on x only. The next is E of x plus y is equal to E of x plus E of y. This is equal to E of x plus E of y. Now Next we consider each of this e of x1, e of x2, etc. e of xn. But note that all these x1, x2, etc. xn are drawn from same population. It's a sample drawn from a population with mean mu and variance sigma square. Therefore, this x1, x2, etc. xn will inherit all the features, all the measures of population. Individually, if you take x1, its mean will be, its expectation will be the expectation of the population, that is mean of the population. That's why e of xi is equal to mu. Individually, if you take variance of xi, variance of xi will be the variance of the population, that is variance of xi will be population variance sigma square. So since all these x1, x2, etc. xn coming from same group, these x1, x2, etc. xn will have identical features. That is, e of x1 will be mu, e of x2 will be mu, etc. All e of these variables will be mu. That's why e of x bar equal to 1 by n, that is a constant outside, and inside the bracket all expectations were replaced by mu. So that's why e of x bar equal to mu. This shows that expectation of the t is equal to mu, or mu x bar is an unbiased estimator of population mean. Now we will get a counter example, that is an estimator not unbiased. For that we consider the variance of sample. This sample variance is an estimator, suppose proposed to estimate population variance. If S square is also an unbiased estimator of population variance, we must get E of S square is equal to sigma square, where sigma square representing population variance. For that, again, we can see from the sampling distribution, that is in chi-square distribution, E of n square by sigma square equal to n minus 1. Shall I say again open the page of chi-square distribution, sampling distribution. Here in chi-square distribution, we have this property that E of n square by sigma square equal to n minus 1. Because n square by sigma square follows chi-square distribution with n minus degrees 1 freedom, and in chi-square distribution, expectation or mean is the degrees of freedom. Therefore, this is chi-square with n minus 1 degrees of freedom. Its expectation will be therefore n minus 1. So here we have the result E of n square by sigma square equal to n minus 1. So again, using the property of expectation, n by sigma square taken outside, so it is 1 minus 1 by n sigma square. So we are getting E of s square equal to 1 minus 1 by n sigma square. It is not equal to sigma square. Along with that sigma square, there is another constant like 1 minus 1 by n. So we don't get s square as an unbiased estimator of sigma square. But here we can note one more property, that suppose n becomes larger and larger, then 1 by n becomes very small. Or when n tends to infinity, 1 minus 1 by n will be certainly 1. That is, E of s square will tend to sigma square, will approach to sigma square where n tends to infinity. Therefore, we can say that when n tends to infinity, E of s square approaches to sigma square, or that is known as asymptotically unbiased. Therefore, E of s square is not sigma square. E of s square tends to sigma square when n is large, or s square is a biased estimator of population population variance, but it is asymptotically unbiased. Now, next is the same property is examined in sample proportion. So we have to examine whether sample proportion is an unbiased estimator of population proportion. So here we consider a set of variables x1, x2, etc. xn representing the responses of the units of investigation, 1 if with the probability p and 0 with the probability 1 minus p. P is the proportion of the population, and we formulate an estimator, that is x by n, where x is x1 plus x2 plus etc. xn. Suppose there is a sample of size 100, and of this 100, some may be 1 and others may be 0. And if x is equal to some 25, it means that there will be 25 times 1 and 75 times 0, that is x equal to x1 plus x2 plus etc xn. So x equal to 25 means that there are 25 times, or the response is 1, response is yes according to 1, and therefore x by n is the sample proportion. So our aim is to show that the sample proportion is an unbiased estimate of population proportion. So it is E of x by n, again using the same property, E of x by n is equal to 1 by n E of x1 plus E of x2 plus etc plus E of xn. But E of xi is 1 into p plus 0 into 1 minus p, that is using this response and their respective probability, and therefore E of xi is p, and E of xi square is equal to 1 square into p plus 0 square into 1 minus p. Therefore it is p minus, therefore variance of xi is p minus p square, that is pq, where q is 1 minus p. So when we replace all these E of x1, E of x2, etc., E of xn by p, it will be n times p divided by n, that is p. Here we note that all these x1, x2, etc., xn are drawn from same population. Therefore, E of x1 will be p, or the proportion of the population p will be E of x1, and the same will be for E of x2, because all these variables are coming from same population. Thus, we get x by n as an unbiased estimator of population parameter p. That is, in short, sample proportion is an unbiased estimator of population proportion. So when we consider here three examples, one is sample mean, second sample variance, the third is sample proportion. Sample mean is an unbiased estimator of population mean. Sample variance is a biased estimator of population variance, but it may be asymptotically unbiased. Sample proportion is an unbiased estimator of population proportion. So the next property is consistency. In consistency, we consider again a statistic T to estimate, say, a parameter theta. Here we consider this consistency property with the help of an example, say Tn. Tn is taken as here x1 plus x2 plus etc plus xn by n. So when this n is 1, t1, it is x1. When n is 2, t2, that is x1 plus x2 by 2. When n is 3, x1 plus x2 plus x3 by 3, etc. Now, Tn is said to be a consistent estimator of theta if Tn tends to the parameter theta when sample size increases. The meaning is that for every sample size, we can calculate an estimate of this parameter theta. When n becomes larger and larger, this Tn becomes closer and closer to the parameter theta, or the difference between Tn and theta becomes smaller. Tn moves in the direction of the parameter, then we say Tn is a consistent estimator of theta. Because the sense of consistency is that Tn is moving in the same direction of the parameter, not any moment going away from that parameter, always in the consistent direction. That's why we say the property consistent. So Tn is said to be a consistent estimator of theta if the difference between the proposed value of the parameter using Tn and the actual value of the parameter theta becomes smaller and smaller when n becomes larger and larger. We can illustrate this with the help of a very simple diagram. Suppose this is a population. Now we draw a sample. Based upon that sample, we propose an estimator of the parameter. Suppose this is a sample we draw from the population. Based upon this sample, we propose an estimator. Now again we make the sample size large. So again we have the estimator. And when the sample size becomes larger and larger, if it becomes closer and closer to the parameter, that means the difference between the proposed estimator value and also the parameter actual value becomes smaller and smaller, or it becomes very close to the parameter, then we say it is a consistent estimator. We can illustrate with the help of an example. That is, here again we consider sample mean to examine consistency. So E of x bar equal to mu. It is already proved in along with unbiasedness. So here an estimator is said to be consistent if E of t is equal to theta or E of t tends to theta when n tends to infinity. Secondly, variance of t tends to 0. So these are the essential properties that an estimator to have to possess the property of consistency. So in the case of this sample mean, therefore, E of x bar equal to mu. So the first condition satisfied is E of t equal to theta satisfied. Here t is x bar and mu is that standing for theta. So the first property satisfied. It was examined along with unbiasedness. We discussed the same property in unbiasedness and it is obtained as mu. So we are not repeating the same proof or the first condition for an estimator to be unbiased. Sorry, not unbiased, consistent. The second condition is variance of t must be or tends to 0 when n tends to infinity. So here therefore we have to show variance of x bar tends to 0 when n tends to infinity. So variance of x bar is 1 by n sigma is equal to 1 to n xi. So it is 1 by n square variance of x1 plus variance of x2 plus etc plus variance of xn. Here we make use of two properties. One is variance of ax is equal to a square variance of x. The second is variance of x. The second is variance of x plus y is equal to variance of x plus variance of y when x and y are independent. So here 1 by n square therefore comes outside and variance of the sum becomes sum of variances because the variables representing sample are independent because we draw the sample in a random scheme. Therefore, never the value of one variable will indicate value of the second variable. That's why we say the sample is random and that's how they become independent. So it is 1 by n variance is 1 by n square v of x1 plus v of x2 plus etc plus v of xn or 1 by n square sigma square plus sigma square because all the variables x1 x2 etc xn are coming from same population. Therefore individually the variable variance v of x1 will be variance of the population and since all are from same population they have all identical variance sigma square. So we have n times sigma square, so it's sigma square by n, 1n cancelled. When n tends to infinity, what happens to sigma square by n? That will tend to 0, which means that variance of x bar tends to 0 as n tends to infinity, or this is like v of t tends to 0 as n tends to infinity. Thus x bar possesses both properties of a consistent estimator. Thus, x bar is an unbiased and consistent estimator of population mean. That is, sample mean possesses both properties of the best estimator. The two rounds already uh, in. Okay, the way the sample mean is in for estimating population mean. So next we can see this sample variance. Earlier we found that sample variance is asymptotically unbiased. It is not biased, but asymptotically, it is not unbiased, it is asymptotically unbiased only. That is E of S square is not equal to sigma square. But we can see that E of S square tends to sigma square when n tends to infinity. That is in unbiasedness, we found that E of S square tends to sigma square. E of S square, this implies that in population following normal distribution, sample variance becomes an unbiased estimator of population variance in large samples only, that is asymptotically unbiased. So the first property of consistency already examined along with that verification of unbiasedness. Next, we can come to the variance of S square. We can see that in sampling distribution, we found that V of S square equal to 2 into n minus 1 by n square sigma raised to 4. That was discussed along with the chi-square distribution. That is here, V of S square is 2 into n minus 1 by n square sigma raised to 4. So it is when n tends to infinity, V of S square tends to 0. Thus we have sample variance is a consistent estimator of population variance. So in the second elimination round, this sample variance is in. So in the first round, that is of unbiasedness, it was out. It was only asymptotically unbiased. It is not unbiased. So sample variance is an asymptotically unbiased and consistent estimator. Next, we can examine another estimator T, which is 1 by n sigma is equal to 1 to n xi minus me whole square. We can show that this T will be an unbiased and consistent estimator of population variance. We note that this T is not like the equation of S square. Here it incorporates one parameter mu. So if mu is known, then only this t is a meaningful estimator, because this estimator is always a function of x1, x2, etc. xn. That is statistic. But if you put this mu here, we can show that that will be an unbiased and consistent estimator. But that t is meaningful, or t can be used to estimate if the value of mu is known to us. It's about the unbiasedness and consistency of mean x bar and also S square t. Next, we come to the sample proportion, consistency of sample proportion. We can see that E of x by n, we already found that E of x by n equal to p along with the unbiasedness. Now, therefore, the first property of consistency fulfilled, that is E of t equal to theta. The second property is variance of t tends to 0 as n tends to infinity. We have V of x by n equal to 1 by n square, variance of summation I is equal to 1 to n xi. Again, using the properties of unbiasedness, now again the properties of consistency, we have 1 by n, I'm sorry, not variant, properties of variant, consistency, properties of variance. We have 1 by n square V of x1 plus V of x2 plus V of xn. So if you replace all these variances by pq, so it is pq by n. When n tends to infinity, V of x by n tends to 0. Hence, sample proportion is a consistent estimator of population proportion. Therefore, sample proportion satisfied both the elimination rounds. Therefore, it is unbiased and also consistent. Sample proportion is an unbiased and consistent estimator of population proportion. Next, we come to the efficiency of an estimator. This efficiency property is considered only for unbiased estimators. Therefore, the estimator already satisfied the first property only will be taken for this verification of efficiency. Suppose T1 and T2 are two estimators, unbiased, for estimating the parameter theta. Suppose their variances are variance of T1, E of T1 minus theta whole square, and V of T2 is E of T2 minus theta whole square, because variance is actually E of x minus E of x whole square. Therefore, this will be V of T1 equals E of T1 minus E of T1 whole square. But E of T1 is theta. That's how we have theta here, because T1 and T2 are unbiased estimators. Now, the estimator with the lesser variance is said to be the more efficient estimator. So, in order to examine efficiency of an estimator, first we will consider only unbiased estimators. And among this class of unbiased estimator, the least variance estimator is said to be the most efficient estimator. What is the meaning of variance is less? Variance less means the variables are almost in the surroundings of this mean, or the differences of the variables or the values from mean are lesser, then variance becomes smaller. Means that if observations are very close to the population mean, variance will be smaller. So efficient estimator is when these observations will cluster around the population mean. So the least variance having estimator is said to be the most efficient estimator. Here we consider a sample of size 3, and based upon this sample of size 3, we propose 5 unbiased estimators: T1, T2, T3, T4, T5, all in different structures. T1 is x1 plus x2 plus x3 by 3. T2 is x1 plus 2x2 plus 2x3 by 5. T3 is 2x1 plus 4x2 plus 5x3 by 11. Again T4 here, T4, T5 is here. You can see that all these estimators are unbiased. That's by considering E of T1, E of T2, E of T3, E of T4 and E of T5. You can show that all these expectations are equal to theta. Therefore, these 5 estimators are unbiased estimators, and therefore they are eligible for efficiency check. Now, next our idea is to identify the estimator having least variance. So V of T1 is 1 by 9 V of x1 plus V of x2 plus V of x3, which is equal to sigma square by 3, because all these x1, x2, x3 are coming from a population having variance sigma square. So therefore it is sigma square by 3. Likewise, for variance of T2 it will be 9 sigma square by 25. Variance of T3 will be 45 sigma square by 121. Variance of T4 will be 11 sigma square by 9. Variance of T5 will be 14 sigma square by 36. We can show that among these 5 estimators, unbiased estimators, the least variance estimator is that of T1. Sigma square by 3 will be the smallest. You can compare it by considering these variances without the factor sigma square, because sigma square is a common value in all the variances. So just use calculator to determine 1 by 3, 9 by 25, 45 by 121, then 11 by 9 and 14 by 36. We can see that among these fractions 1 by 3 will be the smallest. Then the smallest variance is corresponding to the estimated T1, and you note that T1 is the sample mean, because x1 plus x2 plus x3 by 3, this is not the sample mean. It is actually an estimator proposed to estimate. It is not sample mean, but this is an inbuilt function, a default function, that is sample mean. So since sample mean is the estimator having least variance, we say among these 5 estimators, sample mean is the most efficient estimator. So the next is sufficiency. Sufficiency is a little bit analytical property. We say therefore a very simple explanation about the sufficiency. See, an estimator is actually a function of variables representing sample, that is x1, x2, etc., xn. So definitely this x1, x2, etc., xn will contain lot of information about the parameter theta, but that estimation of the parameter is done by introducing a function of x1, x2, etc., xn. Here the real holders of information about the parameter are x1, x2, etc., xn. But those x1, x2, etc., xn are separated by comma. They cannot propose any value for the parameter. So we transform the information belonging to x1, x2, etc., xn using a function of x1, x2, etc., xn, like sample mean or like some sample median, etc. So this is a function introduced to estimate the parameter theta. So when you introduce such a function, a transformation from a x1, x2, etc., xn to a sample mean or sample median is done. The real holders x1, x2, etc., xn has been transformed to a single value, sample mean, sample median, etc. So there may be a suspicion that this information already possessed by x1, x2, etc., xn regarding the parameter theta transformed to this proposed estimator also. If no information is lost for estimating the parameter uh, that was possessed by x1, x2, etc., xn, then we can say this estimator is sufficient. So we don't need the real observations x1, x2, etc., xn. All the information contained in x1, x2, etc., xn are possessed by this proposed estimator also, then Tn is a sufficient estimator. So no need of that x1, x2, etc., xn. Tn is enough to estimate. Tn is sufficient to estimate the parameter theta. We are not coming to the other properties to examine sufficiency of an estimator. That's about the four properties of estimators.